Hello everyone, I'm Jianren Wang from Carnegie Mellon University. Today I'm going to talk about Claude, contrastive learning for unsupervised dynamics. This is joint work with Yujie and Zhao. In this work, we focus on the problem of modeling dynamics in the physical world, which is an essential and fundamental problem in the robotics applications, such as manipulation, planning, and model-based reinforcement learning. Given a state-action-state tuple, the goal of forward dynamics model is to predict the next state from current state and action, and the goal of inverse dynamics model is to predict the action given the initial and target states. To perform complex control tasks in an unknown environment, an agent needs to learn these models from experience. However, developing agents that can learn dynamics directly from high-dimensional observations, such as pixels, is known to be challenging. There are three key challenges. First, learning informative representations of the state from raw images is difficult. Second, the dynamics of real-world objects are always complex and nonlinear, especially for deformable objects. Third, modeling the stochasticity of environment agent system is extremely challenging. The stochasticity mainly comes from two aspects: the noise in the agent's actuation and the inherent uncertainty in the environment, both of which cannot be ignored. In this paper, we introduce a novel method named Claude that uses contrastive learning to handle all of the above challenges. We jointly train a forward dynamics model, an inverse dynamics model, a state representation model, and an action representation model with contrastive objectives. The forward dynamics model is trained to maximize agreement between the predicted and observed next state representation. The inverse dynamics model is trained to maximize the agreement between the predicted and the ground truth action representation. We will go through each module in detail. The benefits of capturing the structure in the underlying state space is well understood and widely used in robotics. Given a set of states, the goal of the representation model is to encode high-dimensional images into informative representations. State representations allow the policy to generate across states. Naturally, such features would be useful later for planning. Similarly, there often exist additional structures in space of actions that can be leveraged. Given a set of action, we introduce an action representation model to encode actions into embeddings. Given a state-action-state tuple, a model that predicts the state of next time step, given current state and action state, is known as forward dynamics model. Instead of directly learning a dynamics model through pixel space, we consider to make predictions in learned latent space. Because making predictions in raw sensory space is hard and can always be distracted by irrelevant information. On the other hand, a model that predicts the action that relates to a pair of input state is called an inverse dynamics model. Similarly, we consider to make predictions in a learned action space. Inspired by recent contrastive learning algorithm, we propose to train these models by maximizing agreement between the predicted and real representations via contrastive loss. Here we use cosine similarity to denote the distance between two representations. We randomly sample a mini-batch of n-state action-state tuples. For forward dynamics model, a prediction and real representation from the same tuple is defined as positive example. We treat the other real representations within the mini-batch as negative samples. Similarly, we define the loss function for inverse dynamics model as follows. During joint training, the total loss is computed across all positive pairs in a mini-batch. We evaluate our proposed method in comparison with classical baseline methods on two tasks: goal-directed planning and imitation from observations on real manipulation. For goal-directed planning, we propose to plan with a simple version of model-predicted control. We calculate the success rate on module co-rope. We also evaluate the performance of our proposed method on imitation from observations. As can be seen from the chart, our method outperforms all baseline methods by a large margin on goal-directed planning and imitation from observations. Here are some qualitative results for goal-directed planning and imitation from observations. Please check our paper and project page for more details. Thank you.